strongly interacting atomic Fermi gases. So, let us welcome Dr. Roati.
Is working this? Okay. So, first of all, let me thank the organizer and the scientific committee for giving us the possibility of presenting here our results. As you see from the title, we are going to talk about dynamics of ultra-cold Fermi gases. Let me turn on this machine. Okay. So after the introduction, the beautiful introduction yesterday by Randy Hewlett and Francesca Ferlaino, I don't need to introduce a lot the interest of ultra-cold atoms. The only thing that I want to mention here that are particularly special system, since you can control in a very nice way the interaction and you can tailor also optical potential where to trap and to manipulate this system. In my case, I want to point out that these are very nice environments where to study strongly correlated fermionic system. How do we do this? And this is common to many experiments that probably you will also listen during this week. We use flashback resonances, and we use two internal spin states of lithium-6, in particular the lowest two, that we can call spin up, spin down, in the future. So I want to also to add a new ingredient, because this was so far not mentioned, that when you consider atomic Fermi gases, this is also true in general also for bosonic system, but anyway, for a Fermi mixture across a flashback resonances will be worth, with resonant so short-range interaction, it is worth to introduce this picture, saying that this system, in fact, features two distinct energy branches. The lower branch that corresponds to an effective interspecies interparticle interaction, and an upper branch that is an excited state that corresponds to an effective repulsion between the particles. So, as you probably can imagine, the lower branch corresponds to the famous and super well established and studied in this system BC-BCS crossover. So the crossover for a bosonic condensate of molecules to a BCS-like Cooper pair superfluid. Meaning that you can cross and you can study in the same system both bosonic and fermionic superfluid passing through this intriguing regime that is the crossover superfluid. On the other side, if you go to study, if you to see what happened in the excited branch, well, in this sense, one can see that this corresponds to effective repulsion between particles, and it has been predicted that in the case of purely repulsive potential, that when I crank up the repulsion between the spin, then I can observe a phase separation between spin down and spin up particle, forming a sort of ferromagnetic state. Remember, this is an excited state anyway. So our weapon, in fact, to study and to attack lower and upper branch dynamics is a particularly simple tool that is a thin optical barrier, whose extension is of the order of 1 over kf, the mean interparticle distance, and then is also comparable, if you want, to the correlation length of the superfluid that we are studying in our system. So this is the outline of this presentation. I will give you, I will show you our results in the lower branch physics studying Josephson effect of fermionic pairs across the BC-BCS crossover. And then I will give you a measurement. I will show you a measurement that we recently performed in the repulsive branch. In particular, I will show you the spin dipole mode of Fermi gases. And then I will come to some conclusion. So just for starting, it is also nice for me to show you our experimental apparatus. This is the only slide that I have for showing it. So we use a practically standard cooling scheme to load the atom in an optical dipole trap. However, we perform D1 Molassa cooling that works very efficiently in the case of lithium-6, following an idea of the group of Christophe Salomon at École Normale. In this way, we are able to transfer more or less all the atoms from the Melassa, the mode Melassa, to the optical dipole trap very efficiently. Then we polarize the atoms in the lower spin state, and then we proceed with evaporation in the optical trap across the flashback resonance. And this is our standard number, so we proceed with, like most of the experiment. So we can produce, if we evaporate in the positive side of the flashback resonances, a molecular Bose-Einstein condensate of more or less 500,000 of molecules. At the same time, evaporating in this region of the scattering length, we can produce degenerate Fermi gases with temperatures that are below 0.1 T over TF. And then if we work at unitarity, we can produce fermionic superfluid. And at the beginning, to demonstrate in our system that we had indeed superfluid also at the unitarity, we perform the same analysis that was reported first in the group of Martinsville and MIT, extracting the equation of state of our gas. So, as I was saying, our tool to attack and to study lower and upper branch physics is a thin optical barrier. So this is an example of what happened when I superimpose to our superfluid the barrier. So you can really see that the system is then separated in two superfluid reservoirs. So I don't have time, and I don't think that it's necessary that I introduce you Josephson effect, that in fact is a very well-known phenomenon in condensate matter system. However, just to say a few words, if I consider a superconductor that is separated by a thin insulating barrier, then I can observe current between the two sides just given by the difference in phase between the two reservoirs. And in case I also have a difference, for example, in our case, in chemical potential, I can observe oscillatory current between the two sides. Well, as you see here, I introduced two variables that are the difference between the Cooper pairs between left and right, and the difference in phase, so the relative phase between the two sides. And you can see that these two quantities can be mapped in this Hamiltonian that is, in fact, the pendulum Hamiltonian, that, in fact, describe completely the Josephson effect. EJ is nothing else than, it's called Josephson tunneling energy, and gives you the strength with which the two phases of the two superfluid or two superconductors are, in fact, connected in the barrier region. And EC is instead the charging energy that is related to the compressibility of your system. Of course, in our case, I mean, to be in the Josephson effect limit, if you want, we must have that EJ is winning against EC, and of course, EJ must be also larger than KBT. Otherwise, thermal fluctuation will scramble the relative phase between the two sides, and then we cannot see any coherent tunneling. And I want also to mention that, of course, Josephson effect has been observed in many, many systems, condensate matter system, and also, of course, in Bose-Einstein condensate. And I mentioned here the work in Florence, Oberthaler, and of course, the group in Israel. So, if you want, this is the same picture than before, but more adapted to what we do, in fact, in our experiment. So we create a potential barrier that is larger than the chemical potential, or comparable with the chemical potential of the two sides. And then, creating a difference in chemical potential, we expect to observe tunneling of pairs at a frequency that is the plasma frequency or the Josephson frequency. And I want to remark also something here that maybe we forget sometimes, that we are working with gas. And so this means that we can access to two quantities at the same time. That is, in fact, the relative population dynamics, taking picture in situ, but also by expanding the two cloud after a time of flight, we can also extract the information on the relative phase, okay, studying the interferogram dynamics. So, I present your data here for a fixed barrier height of around 1.2 the Fermi energy, and these are the data corresponding to the molecular Bose-Einstein condensate. So we started with an experiment that is very similar in some extent to the one of Marcus Oberthaler. The only thing that you have to consider here that the relative imbalance between the two sides is only a few percent due to the strong interaction that anyway we have in the system. Here is the population dynamics versus time, and this is the relative phase dynamics versus time. So both show nice oscillatory dynamics, and as you can see, they are out of phase of pi over 2. We repeated the same experiment, and here I show you only the unitary Fermi gas. In the case of unitary Fermi gas, we observe the same dynamics in the population and in the relative phase. Just let me comment that to retrieve the phase in the case of the unitary and the BCS superfluid, we had to sweep very fast the magnetic field to the BC side to avoid the effect of the collision during the time of flight, as was demonstrated by the group of Wolfgang and Ketterle a few years ago. So we can, of course, the nice thing of this system is that we can tune the interaction across the BC-BCS crossover, and we could repeat the measurement of the plasma frequency, now here is scaled with the trapping frequency. And as you can see, we see a monotonic, non-monotonic behavior with a maximum of the frequency around the unitarity. Okay, in a two-mode approximation, we can say that the plasma frequency is directly related to this quantity, the EC and EJ, by this relation. And EC, as I was saying you before, is related to the compressibility or to the chemical potential. It's a bulk properties that can be extracted in theory by knowing the equation of state of the system. This means that in principle, we can calculate this quantity, and then knowing omega j, measuring omega j, we can extract the behavior of EJ. And this is what we did here. So as you can see, EC is a monotonic increasing function, as you can expect, since the chemical potential should increase going from the BC to the BCS, where it should reach the Fermi energy. But then if I calculate this quantity, I see that EJ is following the same behavior of omega j. So remember, in this experiment that I'm showing you, we are fixing the barrier height. So the increase going from the BC side to the unitarity is, of course, well understandable since we are increasing the chemical potential of the system. However, if this would be true for all the regime, I should see that this quantity should increase. Instead, what I'm seeing here is a decrease of EJ going to the BCS, where instead each EC should, reach, in fact, the maximum value. Our understanding here is that, in fact, we are just observing the fact that the condensate fraction that is, in fact, responsible for the Josephson effect, going from unitarity to the BCS decrease as the gap. While, of course, in the BC, and almost unitarity is almost 1. So this, if you want, is a measurement that tell us how, that is directly telling us how the condensate fraction is moving, going from the BC to the BCS regime. So we wanted to explore also another regime, okay? Suppose that in some way, I can increase now the ratio between EC and EJ for some, in particular, I would like to find a way to increase EC. That means to, for example, increase the imbalance between the two sides or change the barrier with respect to the chemical potential. This is a picture. You see the mismatch is clear also by the in situ picture. And then we see the same dynamics. So in these two data set, I show you the behavior on starting from the 50% of imbalance from both BC to the crossover superfluid. So we see in both cases, we see an initial decay. And then if you do time of flight at this time of evolution, we start to see vortices appearing in the superfluid. But then, if I let the system evolve even more, then what I see is that the system starts again to oscillate a la Josephson. I want to mention that a very similar work has been observed in a group of Campbell at NIST, okay, in a different configuration with a Bose-Einstein condensate of rubidium. Anyway, the message is that Josephson dynamics seems that can be restored after phase leakage processes that in our case are vortices, then decaying phonons. And this is also we have a confirmation of these dynamics also by Gross-Pitayevsky simulation in the case of a molecular Bose-Einstein condensate. And I want also to stress that what we see is a little bit different with respect to what is observed in the experiment at ETH in the Esslinger group, where instead the, let's say, dissipation is induced by Andreev reflection in a quantum point contact. So the geometry is different. And in our case, we just see vortices. And the vortices that we observe are probably very close to the one that were observed in the group of Martin Zvirline and Gabriele Ferrari in Trento. And in fact, we had in the previous work a characterization of the period of these vortices rescaled to the trap frequency. And as we see, as Martin was observing, we have an increase going from the BC to the BCS side. Well, in the last 5.56 minutes, I will try to give you an overview of what we did in the case of the upper branch dynamics. So when you start to mention repulsive Fermi gases, of course, it is very complicated to mention all the work that has been carried out in the last year, both in the experiment and, of course, in theory. So it's a quite hot topic, and people are still exploring all the possible situation in this case. So I just use a sentence of Professor Ketterle that, of course, you can ask yourself, in what extent we can prepare and study an atomic system with such short-range interaction and neglecting the fact that you have, in fact, also the bound state, that is the ground state of your system. Well, in fact, as was pointed out by the group at MIT, the problem is that the system is not stable. I mean, as soon as you start, here is stable. In fact, you can have a weakly repulsive Fermi system. But then as soon as you start to crank up the interaction, you want maybe to reach a point in which the system could phase separate. Before reaching this point, the system has 4 molecules and via 3-body recombination, and you are occupying, indeed, the ground state. So you have lost your possibility to stay there. However, one possibility, you have to remember that here I was starting from a situation where the system was, in fact, preparing a sort of paramagnetic state, so up and down the spin were completely mixed. So, of course, to reduce also the possibility of molecular formation, you want to reduce, in some way, the overlap between up and down spin. Okay, I can then ask myself another question. What could be the fate of an artificially prepared ferromagnetic state in the upper branch and vary the interaction, okay, before it melts in some way? Maybe forming molecules, polarons. This is something that can happen anyway. Well, ideally, you would like to start like this. So you would like to start with all particle up spin on one side and all down particle in another side, and then to see what happens when the referee say, okay, let's go. So if you want, this is, in fact, our realization. This is our initial state that I can call an artificial, and is artificial, in fact, ferromagnet. This is a picture, and these are the experimental data. So these are all up spin on one side and all down spin on the other side. And of course, also here, we make use of the thin barrier that we have realized for Sarin-Josephson effect. And how to produce this, if you want, I can tell you. How we can really prepare it 100% up and down experimentally. What is very important is that we can produce a quite cold cloud, and the separation is just given by few interparticle spacing. So this is our starting point. I will show you only one measurement that we perform in this condition. And in particular, we wanted to study the spin dipole mode, that is the out-of-phase mode of up and down spin, once the barrier is released, and it is released suddenly. Why is it interesting to study the spin dipole mode? It's a collective mode, and as was shown in this work by Sandro Strengari and Alessio Recati, the spin dipole mode frequency gives you information about the spin susceptibility of your system, and as you can see, this quantity is expected to increase, eventually to diverge at the transition to the ferromagnetic state. And surely what you expect to see is a softening of the spin dipole frequency approaching the critical value of repulsion. So these are our data. So these are 3 examples of spin dipole oscillation. I want also to mention that since the 2 clouds are almost separated by a few microns, the relative momentum with which they collide is very small with respect to the Fermi momentum. And this is another important difference with respect to previous experiment. Anyway, we see here the transition of this, the relative displacement of the center of mass versus time for 3 different values of interaction: weakly repulsive, almost at the transition as was expected by the theory, and over the transition. And here, I report just the plot, with all the data, in which we renormalize then the spin dipole frequency with the trap frequency versus KFA. So this, we see a clear softening of the mode, and around 1, we start to see a jump of the spin dipole mode frequency to a value that is 1.7, the trap frequency, almost like if the 2 clouds oscillate in half of the cloud. So it means like if the 2 clouds are really bunching against to the other. And this value here is in a good agreement with the previous experiment carried out at MIT. So the green curve here are the are the theory extracted from this work, in fact, but also calculated for a closer situation that we have in the lab. So this, the dotted line is exactly the 100% overlap. That is what we don't have, in fact. And this is close to the other value, the 25%, is closer, the situation that is closer to what we have, in fact, in our experiment. And our data are, lie in the confidence region. And also here, I want to tell you that we have two kinds of measurement for different temperature, okay? And as you can see, for higher temperature, the transition to this jump in the spin dipole mode happens to larger repulsive interaction. I want also to mention that there is a nice work, a related work with bosons, so with spin dipole mode in boson recently appearing in the group of Gabriele Ferrari in Trento. I have just one slide more. So, of course, we wanted to do something more, also to confirm that our dynamics, that is here in red, was really related to upper branch physics. And so we redid, with slightly different protocol, the measurement starting in the lower branch. And here, you expect that the spin susceptibility going from the negatives to the positive side of the flashback resonances eventually reaching the molecular VC should decrease, meaning that the spin dipole mode frequency should increase. And these are our data points, and the shaded purple or blue line here, blue area, is obtained using data from the group of Tajima and Hohashi of the lower branch spin susceptibility. So this means that, we observe a completely antagonist behavior in the dynamics of the upper branch and lower branch spin dipole mode. So I come to the conclusion. We are carrying out experiment in the lower and the upper branch across a flashback resonances. I hope that I could convince or convey you the message that we studied Josephson tunneling and dissipation now also in this system. And we are now in these days, exploring, in these months, in fact, we want exploring repulsive Fermi gases, hoping that we can find evidence of ferromagnetic instability in this system. I want also to add that we are recently carrying out work together with Pietro Massignan at ICFO, observing finally repulsive lithium-6 polarons. These are examples. I don't have any time to enter in any detail. But anyway, we have clear evidence of the presence of repulsive polaron in lithium-6. And now the system is also ready to enter in 2D, with TM01 mode at this moment. And here, we would like to study superfluidity spin dynamics, as we did in 3D system. So let me acknowledge the people that work in this project. In particular, I want to mention Matteo Zaccanti, and of course, Giacomo Valtolino, that is here, that was and is the main person that, in fact, was fundamental for all the work that I was showing you today. Thank you so much.
Thank you for the talk. So, is there any question or comment, please? Raise your hand.
Good.
Yes, over there.
Giacomo, when you measure the phase of the two parts of the superfluid in your Josephson junction experiment, what determines the contrast? It seems the fringes were sort of rather low contrast. Is that due to interactions or what?
I would say that probably are due to still to interactions. So probably we are not. We try to sweep as fast as we can. We sweep in around, I think, 150 microseconds, but probably we are still limited by interaction in our system.
Is there other question from the audience? If not, then let's move on. Thanks. Yes, okay, sorry.
Francesca.
Hi, Giacomo. Great result. Congratulations, first
Thank
of all.
you, Francesca.
So I'm not very much updated in the physics of unitarity Fermi gas anymore. I just had the curiosity. So when you make the relation with the gap in the, let's say, BCS state. So here, I mean, in mapping the difference in the phase and so on, so there is the assumption that the wave function is not modified across the crossover, or so could you comment on how, so is this wave function fixed? Because I would naively expect it should change, I don't know.
What I can tell you is that okay, there is no work at the moment that I am aware of, in theoretical work, that in fact study the Josephson dynamics in the unitary limit. And as the evolution of this coupling, Josephson coupling energy, EJ in particular, is behaving, crossing from, if you want, BC to the BCS. So what we found is that the only thing that we can say is that in the BCS superconductor at equal 0, there is this Baratov formula that just tell you how the Josephson coupling term should scale with the gap. And so we assume that we can use the same argument to give an interpretation why our data show, in fact, a decrease in, if you want, the plasma frequency and at the same time then in the coupling Josephson. So it's an assumption.
Okay, so let's thank the speaker again, and let's move on to the next speaker. So final talk in this session will be from Dr. Subhadeep Gupta from University of Washington, USA.